Sure, we looked at discriminant based classifiers, right? So maybe as a quick recap, I think we have seen three different classes of classification algorithms, right? Like, so starting from generative models, right? So then discriminative models, then discriminant based models. So, well, as a review, can someone tell me the difference between these three families of algorithms? So what does a generative model do? Yeah. Yeah. So in general, like the idea here is to model P of x comma y, right? So generative models model the joint distribution P of x comma y, and the way in which we do this is like, so we try to model P of y and P of x given y, right? And then we use the Bayes rule to flip the conditional and compute P of y given x. So can you give me example algorithms for generative models that we have seen? Yeah, GDA is one example, right? Okay, now what are discriminative models? Like, so what do discriminative models do? Someone else? Yeah. Yeah, so they directly compute P of y given x, right? Instead of modeling the joint distribution. So you cannot generate examples with discriminative models because it's only giving you P of y given x. There is no P of x. If you have P of y given x and P of x, then you can combine them together. Similarly, if you have P of y and P of x given y, then you can combine them together, right? Like, so in this case, you are just modeling P of y given x. So can you give me example algorithms for discriminative models? Logistic regression. Okay, so anything else that we have seen so far? Yeah, KNN, right? Okay, so what are discriminant based models? Sorry? So you are directly mapping x to some class label, right? Like, so these are something like y is equal to f of x. And the most important distinction is there is no probabilistic interpretation for discriminant based methods. Like, so it's not based on probabilities, it's just some scoring function, right? So what would be the example for discriminant based method? Yeah, linear regression is one example. Like, anything else? Well, if you're using linear regression for classification, right? Like, that's one example. Any other classifiers we have seen so far? SVMs. Okay. Anything else? Perceptron, right? Okay. So in the case of SVMs, we discussed two formulations last week, right? Like, so we actually started with hard margin SVMs, right? And then we relaxed certain constraints to make it soft margin. So specifically, we used the idea of slack variables to reduce, to relax the constraints, like, and get hard margin, like soft margin SVM, right? Like, so now, can someone tell me the difference between these two formulations? Like, so why do we need a soft margin SVM? Yeah. Sorry, can you? It allows to have incorrect classifications. Like, so why is that necessary? Yes, if the problem is not linearly separable, then hard margin SVM will not converge, right? So because hard margin SVM makes this assumption that the problem is linearly separable. So when the problem is not linearly separable, the penalty is going to be infinite, right? Like, so for hard margin SVM, so there is no solution, which is why we introduced the idea of slack variables. So the slack variables really allow some leeway in the sense like it says, oh, you can have some slack in classifications, like you could misclassify a bit, and then we try to reduce the strength of the slack as much as, like basically the sum of the slack as much as possible, right? Like so in some sense, like we're putting a soft constraint on avoiding misclassification instead of hard constraint. Is that clear? Now, in the past, we have looked at different kinds of error functions, right? Now, however, for doing SVM, we did not start from an error function. Like we actually start from some sort of constrained objective, and we derived the software, like the primal or dual version, right? Like so. Now, what is the error function that SVM is trying to model, minimize, right? So we're going to look at the error function for SVM, okay? But before we do that, like let's try to understand what slack variables are really doing, right? Like so, let's say I have a margin like this, right? For and we have a bunch of data points. Of two different colors. Okay. Now, for any data point that is lying inside this margin, so what would be the slack value? What would be the epsilon for this data point? 0. For this data point is also 0, right? Now, what about this data point? So, what can you say about the slack value for this data point? It's between 0 and 1, right? So, it's something less than 1. And what about this data point? It's greater than 1. Like so, once you are crossing the boundary, then the slack is greater than 1, right? So, in general, for points on the correct side of the margin, right? So, which means y of n times t of n is greater than or equal to 1. Yeah. Yes, it's going to be 2 and then more than 2. Okay. For points that are on the correct side of the margin, epsilon n is actually 0. Okay. So, for remaining points, right, epsilon n is actually 1 minus y of n t of n. Okay. So, for example, for this one, so y of n times t of n is still going to be positive, right? Like it's between 0 to 1. So, this value is going to be less than 1. For this one, it's misclassified, right? So, which means y of n times t of n is going to be negative. So, 1 minus y of n t of n is going to be greater than 1 because 1 minus some value, right? And it just grows in the other side of the problem. Is that clear? So now I can actually combine this two to come up with an objective function. So the SVM objective function can be written as summation n is equal to 1 to capital N. Okay, the error function which takes y of n t of n plus lambda times this, okay, where ESV of y of n t of n is given as 1 minus y of n t of n plus. Okay, so I'm introducing a new operation here. Like so, whenever I do something like this, it just means max of 0, comma whatever the value is. Okay, so this error function is going to be 0 whenever this is negative, right? Yeah, and whenever it is positive, Yeah, 1 minus, okay, when things are correctly classified, this is going to be 0, right? Or negative. So that is 0, otherwise like you have the error function. Okay, so this ESV, right? Like, so this loss actually has a name, so this is called hinge loss. Okay, so this loss, if I go back, hinge loss is going to be 0 whenever things are correctly classified. Whenever things are wrongly classified, then the loss is 1 minus y and tn. So I want to minimize this as much as possible. Is that clear? Any question? So the loss is almost, well, it is exactly linear, right? Like, so it's like a linear loss when things are wrongly classified and 0 loss when things are correctly classified. Okay? Okay, so now we have seen a bunch of loss functions in the course so far, right? Like, so we can actually try to compare all these different loss functions. Okay. Now, well, there are different loss functions here. I want you to guess what each of these loss functions are. Okay, so let's maybe start with this loss function, right? Like, so whatever I'm drawing, right? Like, so what is this loss function? Maybe I'll try to highlight it. So what is this loss function? So the loss is 1 for misclassification and then 0 for correct classification. Yeah? What is this? So that's our usual 0, 1 loss, right? So the step function that you see here is the misclassification error, like 0, 1 loss function. Okay. Now, what about the green one? What kind of loss function is this? Yeah. Well, yeah, it's a square error, right? Okay. First of all, what are the different loss functions we have seen so far? So we have seen square error, misclassification error, which is actually the ultimate loss function that we care about, right? So then, what else we have seen? Well, we saw hinge loss today. What else? Yeah, so logistic regression error, right? Like, so these are the 4 different loss functions we have seen so far. So the green is actually the squared error. Okay, so what about blue? So the blue, when things are correctly classified, the error is 0. Okay, when things are wrongly classified, the error looks like a line. So what loss function is this? This is hinge loss. Okay, and the red that you see here, that is actually the logistic regression error. Okay, so as you can see, all these loss functions have different characteristics, right? So the first thing I want you to remember is, in any classification problem, what we really care about is 0, 1 loss. So we don't care about having minimum square error or minimum logistic regression error or minimum hinge loss. Okay, so for any application, we care about reducing misclassifications, right? Like, so in the end, like, all I care about is, like, I want a classifier which doesn't have any misclassification, right? I want to reduce the errors as many as possible. And the best way to count the errors is just misclassification. Like, so you put 0 when there's no error and 1 when there's an error. And you want this 1 to be as few as possible, right? Like if you have 1,000 examples in your test set, you want the misclassification error to be 0, right? Like, so if you are making mistakes on 100 out of 1,000, then those are the errors where you put loss of 1, right? So in general, we care about misclassification error, okay? However, different classification algorithms use different errors. In fact, none of the algorithms that we have seen so far is directly trying to optimize misclassification error. Can you guess why? If this is what we care about, shouldn't all the algorithms try to minimize misclassification error? Like, why is logistic regression trying to minimize NLO? Like, so why is SVM trying to minimize hinge loss? Any thoughts? Yeah. We cannot compute gradients easily, right? Like it's first of all, the step function is not differentiable, right? But that's not the problem, okay? Because like, so it's not differentiable only at this point, right? The most like the deeper issue here is like, even if you can differentiate, like the step function has very sparse gradients, okay? So the gradients are 0 almost everywhere, and things like, I think we saw this in the perceptron example, right? Like, so in perceptron, like I showed you that like for a long time you might get 0 gradients, like your gradient changes only when one misclassification becomes correct classification, right? So in general, it is really hard to optimize misclassification error, okay? Simply because, well, the 0, 1 loss is not continuous, okay? So all the other losses that we have seen, and also the future losses that we are going to see in this course, okay? So they are all, in some sense, continuous approximation of 0, 1 loss, okay? So if you look at it, logistic regression or square error or hinge loss, they are all continuous approximations of hinge loss, okay? So about the differentiability of step function, right? Like, so if you look at the hinge loss, right? So even that has like a little bit of like non-differentiable part. So when things are 0, right? Like, so that is not the issue. Like, so the nice thing about hinge loss is like you can still optimize it because there is a linear component where you can easily make progress. Is that clear? Now, once you start looking at all these loss functions as continuous approximation of 0 and loss, or in some sense like proxy for 0, 1 loss, right? So now you can try to understand the differences between these loss functions, okay? So which is a good proxy, right? So now can you tell me if square error is a good proxy for step function? That part is okay. So when your error is big, like like, so error being big in this part is okay, okay? So the problem with squared error is it's actually giving you some error even when things are correctly classified, right? So the big problem with squared error is it wants the prediction to be exactly matching, right? Like, because you're doing whatever prediction minus target the whole square. For that error to become 0, the prediction should be exactly equal to target, right? So just for this particular place, your square error is 0. Interestingly, even when things are correctly classified, instead of predicting 1, let's say I predict 5. We know that in classification, anything greater than 1 is class 1, plus when you're doing +1, -1, right? So it actually doesn't matter whether I'm predicting 5 or 10 or 50. However, for square error, it actually matters. Like, so if instead of predicting 1, if you predict 2, squared error gives you some error, right? This is why squared error is a bad error function for classification. It's a great error function for regression, but when you come to classification, squared error is not a good error function, like because it's just not a good proxy for step function. A good proxy will have similar trend as the step function. Okay. Now, what about logistic regression and hinge loss? So hinge loss is nice because when things are correctly classified, the error is 0. Okay. When it is wrongly classified, the error is linear. Now, about logistic regression error, like so when it is wrongly classified, it looks almost linear, right? So the green line is almost linear. It is just that even when things are correctly classified, logistic regression is going to have very small error. But this error decreases. So it's not like logistic, like it's not like squared error. Is that clear? Also, this is kind of consistent in the sense whenever things are correctly classified, the error is lower than wrong classifications. That is not true for squared error. For squared error, even when things are correctly classified, the error is higher, right? So for logistic regression, the error is monotonically decreasing, which is needed if you want it to be a good proxy for step function. Like you want the error to decrease. You want the error for positive classification to be lower than the error for negative classification. Is that clear? Any questions about these different loss functions? Now, you might wonder how people actually came up with these different proxies for loss functions, right? Like, so I think one thing to remember is even though we try to unify all these things in a course, like most of these algorithms were actually developed independently, like in fact in different decades, right? Like the perceptron error criteria was developed in 1950s, right? Like so I don't know when logistic hinge loss is like 90s, right? Like so I don't know when logistic regression error was developed, probably in 70s or 80s, right? So these methods were really developed by different people, like in different periods of time, and they were all trying to solve the classification problem. It is just that they took different approaches, like which resulted in different proxies for the zero loss function. Is that clear? Okay, so that is good. So now let's also talk about another way of classifying machine learning algorithms, like so, which is basically through the lens of parametric versus non-parametric methods. Okay, so typically parametric methods for machine learning would have finite number of parameters. For example, logistic regression, right? Like so it's a parametric method because it has a finite number of parameters, and you're learning these parameters from the data, right? On the other hand, there are non-parametric methods for machine learning. Okay, so the word non-parametric method is confusing. It doesn't mean there are no parameters. It actually means there are infinite number of parameters. Okay, now the best example is k-nearest neighbor. So in k-nearest neighbor, so what are parameters in k-nearest neighbor? No, that's a hyperparameter. Yeah, the data points, like so k-nearest neighbor is an interesting classification algorithm because the parameters for kn is actually the data points, right? Like so if you have 100 data points, you're storing all the 100 data points in the memory to make prediction, right? Like so which means the 100 data points are a parameter. Now, if I give you a million data points, then now you have million parameters. Well, it's not even millions, million times d, where d is the number of features, right? So I could give you 100 million data points. Now you have 100 million times d parameters, right? Like, okay, and then this is why we call these, in theory, infinite number of parameters, because as the data grows, the number of parameters also grows for non-parametric methods. Okay, so which brings us to the second distinction, which is for the parametric methods, the number of parameters is actually independent of data size, data set size. Okay, which is actually a nice thing about parametric methods. Like, for example, let's take logistic regression. If I have 100 features, the logistic regression is going to have 101 parameters, right? Like the features plus the bias, right? So it doesn't matter whether the data set is 1,000 examples or 100,000 examples or a million examples. It's always going to be 101 features, which is not the case for non-parametric methods. In non-parametric methods, the number of parameters is dependent on the data set size and also the complexity of the data. Okay, so examples. So example for parametric methods like are things like GDA, logistic regression, the primal formulation of SVM. Okay, now example for non-parametric methods that we have seen so far are k nearest neighbor and the dual form of SVM. If you remember, in the primal form of the SVM, the equation was equation in terms of W, right? However, for the dual form of SVM, the equation was based on the support vectors, right? Now, if you have a really complex problem, then the number of support vectors might increase. So based on the complexity of the data, you could have more parameters in non-parametric. Is that clear? Any question? Okay, so we will see another non-parametric method today, like after the first half. Okay, so we're going to look at decision trees, which are another example for non-parametric method where the number of parameters actually grow based on the complexity of the data. Is that clear? Okay, so now I want to go back to the discussion on generative versus discriminative versus discriminant based methods. Okay, we are going to talk about when to use what, like what are the trade-offs. Okay, so first let's start with generative models. So generative models typically model the joint distribution P of x comma y, right? And there are many ways to do this. Like one way that GDA and naive Bayes does is basically to model P of y and P of x given y, and then we will use the Bayes rule, okay, which says P of y given x is equal to P of x given y, P of y by P of x. Okay, now there are many advantages of having a generative model. Like, so for example, like one of the use cases, like we could actually generate synthetic examples. From generative model. So can someone explain how you would generate synthetic examples if you have access to P of y and P of x given y? So how would you generate synthetic examples from a generative model? Yeah. Anyone? Yeah. But for that, you need y first, right? Yes, but if you want to generate x given y, you need to sample y first. No? Yeah. So if you want to generate 100 examples, like what you're going to do is, like for each example, you'll first sample from p of y some value, like +1 or 0 or 1 or +1 or -1, whatever. Let's say 0 or 1. Okay, so you'll sample either 0 or 1. Now, conditioned on this y, you're going to generate x. So you will sample from p of x given y. Is that clear? So you just repeat this 100 times, you're going to get 100 x comma y pairs. Is that clear? So this is one application, right? Like, so the other application is you can actually use p of x, if you have access to p of x, for outlier detection. Okay, if you can compute p of x, then given a new data point, you can actually compute p of x for this new data point, and like if that value is too low, then it is an outlier, right? Like, so if the value is too low, it means that this is a very rare example. So sometimes it's useful to know whether something is an outlier, because then you can fall back to human for classification. Like, you can just say that, oh, this looks like something that is an outlier. Like, I don't want to make classification because I might make mistakes. Let's bring a human to do this classification, right? Like, it's useful in critical applications, like where you don't want to make wrong mistakes, right? So you can use p of x for outlier detection. And once you have these probability values, you can also use that to measure model uncertainty. You can know how certain is the model in its prediction. Okay, so there is actually difference between p of y given x being 0.6 and 0.9, right? Like, anything that is greater than 0.5 is class 1. That's what we do for classification, right? Like, however, if the p of y given x is 0.6 versus 0.9, like, so what can you infer? The model is just more confident with the second example because the probability of y given x is 0.9. So it's more confident that it is class 1 versus something like 0.6 or 0. For example, when the model says 0.51 probability, right? So now you can actually use this information and say, oh, maybe I don't want to make the classification now because it's almost 50-50, right? So you can measure some sort of uncertainty of the model's prediction when you have access to the probabilities. Is that clear? Any question? Yeah. Well, if you have access to p of y and p of x given y, you could compute p of x, right? So you just need to marginalize y from p of x given y, p of y. So if you have access to these two things, then that is actually equivalent to having access to the joint distribution. So then you can ask any probability question that you want. You could ask what is p of x, you can ask what is p of y, you can ask what is p of y given x, you can ask what is p of x given y. You should be able to answer all these questions. Okay? Okay, so traditionally, for maybe let me do the discriminative models first, then I will go back to the anecdote. Okay, let's look at discriminative models. Okay, so the nice thing about discriminative models is just that they are simple. Okay, so for example, let's take this classification problem where it's a two-class classification. It is just that the p of x given class 1 is bimodal distribution. So what do I mean by that? Like, it has two modes. It's a bit more complex distribution to model, right? So which means when you're doing generative model, if you're fitting a Gaussian is going to be a bad approximation for this distribution, right? Like, you need something that has bimodal. Like, maybe you need a mixture of Gaussians, like where you have two Gaussians like fitted together, right? Like, so basically, like, you need to have more complex distributions when the data is complex, right? However, if you look at the decision boundary, The decision boundary between blue and red is actually very simple. If your goal is to just classify between blue and red, should it matter that blue is bimodal or trimodal, right? Like, so it doesn't matter. Like, as long as blue is separable from red, right? Right? Like, so I don't care how the distribution of blue looks like. Okay, which is why logistic regression kind of models are more attractive, because they don't care about P of x given Ck, like they just care about P of Ck given x. And sometimes this is actually very simpler to model than modeling the distribution of the data. Is that clear? So, so now a little bit of anecdote here. Like, so for a long time, people were favoring discriminative models over generative models simply because, well, it's easier to train discriminative models. And for a lot of classification problems, you don't need a generative model, right? Also, it's hard to train a generative model because generative models, like, well, we have seen simple generative models in the class, like naive Bayes, right? If you go for much more complex generative models, then either they have more parameters or they are very complex. The distribution is very complex. Fitting data is hard, right? Like, or they just require way more examples. Because you're trying to model the joint distribution, you would need way more examples than just modeling P of y given x. Okay, so for all these reasons, like I think for a long time, like people were preferring simple discriminative models over generative models. However, interestingly, in the last 5 years, generative models became more and more popular simply because there's a lot of data available now and also compute, right? Like, so we made huge progress in coming up with web scale data sets, right? Like, so now if you want to train a model for language, like you're training using the entire web, which has trillions of tokens, okay? And if you want to train a video model, you could just access all the videos that exist in YouTube, which is humongous, right? Like, so there are hundreds of thousands of hours of videos in YouTube, right? Like, so now you could just use all these data to train a generative model, right? Like, and the same is true for images. Like, we have so much images that are publicly available, like that you could actually train an image model, like with all these data sets, right? Like, so in some sense, the idea of generative models, like, became more popular in the last 5 years thanks to data and compute, like GPUs and CPUs that are faster and faster, right? Like, so, like, which is the core machinery behind all the language models that you see so far. Okay, so things like ChatGPT or Gemini, right? So these kind of language models are inherently generative models. Okay, so the way in which they generate the data, right? So why do we call them as generative models? Is because they are essentially trying to model the probability of the joint distribution of words, for example, like in the case of language models. Okay, for example, if you have a document, like just as a cartoon example, like if you have a document which has 5 words, okay, then essentially language models are trying to model P of W1 to W5. Okay, now you can actually model this using the chain rule. So how? You can actually first model P of W1, then you can model P of W2 given W1, right? So then you can compute P of W3 given W1, W2, then P of W4 given W1, W2, W3, then P of W5 given W1 to W4, right? So in some sense, given a sequence of words, you are trying to predict the next word. And you keep doing this for lots and lots of data. Like, so for trillions of like tokens, like, so you're trying to predict, given the context, what is the next word? Given the context, what is the next word? Given the context, what is the next word? Right? When you get really good in doing this, like, so you are, like, when can you get really good at doing this? Like, so when can you perfectly predict the next word given the context. You can do that only when you have really modeled the distribution of words, right? So the benefit of training a large model like with just the simple next, like what people call next token prediction, is if you do next token prediction really well at web scale, then you're implicitly training a generative model. Like you're implicitly training a model which models the joint distribution of the entire text data. Is that clear? So the benefit of training such a model is once you have such a powerful model, like which can model any text, any classification task you want to do, you can fine tune this model for the classification task, right? And you can also do much more impressive things like what the companies are doing right now. Like, so for example, I think most recently, both Google and OpenAI participated in the International Mathematical Olympiad competition. Like, so their language models solved all the problems in Math Olympiad. And this is not just modeling text, right? Like this is actually problem solving skills, like and coming up with solutions for really hard math problems, etc. And and people are doing much more impressive things with these generative models. So for example, mathematicians are starting to use these language generative models as assistants for coming up with completely new proofs or solving open conjectures, right? Like so there are a lot of interesting things that you could do once you have a very powerful generative models. Is that clear? But before you learn about how to train such models, like it's important that you understand the fundamentals of generative modeling, like which is what we did in the last couple of weeks, right? Like so, like with GDA kind of approaches, right? Like so after taking this machine learning course, like so once you go take a deep learning course as a follow-up, right? Like so you will learn about language models and other things. Is that clear? Okay, so I'll do. I'll also quickly cover discriminant models, base models, and then we will take a break. Okay. So yeah,
what's the purpose of discriminative model then? I mean, in the today economy of
that's a good question. So what's the point of discriminative models when you have these powerful generative models? In practice, for 95% of industrial applications, you don't need a generative model. Okay, so the power of discriminative models is really they can be much smaller and much more efficient. So generative models become powerful only when they are huge. Like so, for example, like it's common for these language models to be like 100 billion well, 100 is even small. Like 70 to 700 billion parameter models, like sometimes even trillion parameter models. Okay, now it's just not practical to run a 700 billion parameter model for a simple classification problem that you want to do in your mobile phone, right? Like you might have an app which where you scan things and it tells you where an object is located, right? Like for example, let's say there's an app which scans the room and tells where your keys are, right? So you don't need to run a 700 billion parameter model or 70 billion parameter model to do this. You can actually do this with just less than a million parameters. Okay, so I think there is still a lot of value in learning about discriminative models and training discriminative models. In fact, one of my big complaints about all the recent startups is, well, I think VCs want to give money when you say I'm doing Gen AI, right? Like so, like people try to build generative models for a lot of problems where generative models are overkill. For a lot of these problems that companies are trying to solve by getting millions of dollars of funding, you could solve these models problems with simple discriminative models. So if you want to solve some problems in the future, like so you should first think about whether you can train a simple discriminative model to solve the problem. And if it has 98% accuracy and you're happy with 98% accuracy, you should go for it because you will save a lot of money. Because most of these generative model applications, you're paying a lot of money to OpenAI and Google for the API calls. Okay, so your solutions, if they depend on OpenAI's generative model, right? Like so every time you call the model, you're paying them certain dollar. Okay, so think about how much money you can save if you can train simple discriminative models in-house, right? So yes, generative models are impressive, but they are impressive for different kinds of applications. Like if you want to do, if you want to tackle really hard problems like solving open conjectures or searching the entire literature to find potential drug candidates for a problem, right? Like so, those kind of things you could use generative models. Like a lot of people use them for coding. I don't know how many of you use Copilot for coding, right? Like so, like it has become very common now, right? Like so, it's still an overkill, but if you use it smartly, then maybe it's a good tool, right? Like so, there are a lot of interesting applications where generative models are useful, but for 95% of industrial applications, which is actually what makes money, right? Like so, you don't make money by solving a conjecture. You actually make money by solving an industrial problem, like which could be as simple as detecting defects in a steel plant, right? This doesn't require a generative model. Like a simple discriminative model would do the job. Okay. Okay. So well, maybe let's take a 10-minute